Chapter 4, Engine Basics. We need to learn the terms that describe the basic engine and the roles of each subsystem as they play in the engine management. And we're going to go over 7, actually 8 or 9 subcircuits the engine has been divided into. Engine displacement. We have some simple formulas that will help you go from cubic inches to liters, and the difference between the square, under square, and over square engines, and the mean effective pressure and how that affects engine power. Learn the differences between naturally aspirated and turbo manifold boosted engines. Naturally aspirated engines are still in utility engines and also in the transport refrigeration that we see in Thermo King and Carrier on trailers. The term volumetric efficiency and how it applies to the breathing of the engine, and how some of the physicists' Boyle's and Charles' laws apply to engine operation. How friction and inertia factors play into engine operation, and how the heat energy of the fuel is converted into kinetic energy or work. How rejected heat and thermal efficiency factors affect the life and power of the engines, and explain why it's desirable for an engine to produce peak cylinder pressure at 10 to 20 degrees after top dead center, that's ATDC, and that is approximately 3,000 psi when we have full peak cylinder pressure. The term scavenging, and as it applies to both 4-stroke and 2-stroke diesel engines, and some of the basic characteristics of diesel fuel. We're going to begin with some basic engine terminology. Technicians need to understand how these apply and to become familiar with some of the language that's used in its operation. The engine is an air pump that adds fuel and converts one form of energy to another, and the potential heat energy of the heat engine, potential heat energy of combustible fuel into mechanical work. The internal combustion engine is the combustion of fuel contained within the cylinder, and the diesel engine is also called compression ignition, how the cylinder fuel air charge is ignited by the heat of compression. Kinetic energy, energy of motion, the heat attempts to convert the energy available into a fuel to do mechanical work, and there's some heat loss is the result. Top dead center, when the piston is at the topmost travel. Bottom dead center, when the piston is at the lowest point of travel. And before top dead center, any point of the piston travel through its upstroke. After top dead center is the point where the piston is just past top dead center, is beginning the downstroke. The bore of the cylinder, we're going to get into cylinder bore and cylinder stroke and how that affects the performance and operation of the engine. The bore of the cylinder, inside diameter of the cylinder, starting from where top dead center and bottom dead center occurs. The stroke is the difference between where the top dead center, the top of the piston, is at the highest point and when the piston is at the bottom dead center. All of that is configured into the engine volume. The swept volume is the actual area that is traveled from bottom dead center to top dead center, and the clearance volume is where the engine cylinder is at the top of its travel or top dead center. That's the remaining volume that's in the cylinder when it's at top dead center. The cylinder volume is the total volume from bottom dead center and the swept volume plus the clearance volume. The engine displacement, the swept volume of all the cylinders expressed in cubic inches or cubic in liters. A square engine is an engine that has the same cylinder diameter and the same stroke. So we're going to have the same bore and the same stroke. Those dimensions would be equal. An over square engine describes an engine where the cylinder bore is larger than the stroke, but The undersquare engine is used to describe an engine where the cylinder bore diameter is smaller than the stroke dimension. Compression ignition is an engine that produces the heat generated on the compression stroke. We have approximately 600 psi in a compression ignition engine. Spark ignition is our common automotive engine, where we have a timed electrical spark, and direct injection engine, where the fuel is injected directly into the cylinder. In modern engines, the direct injection is timed by electronic control module that controls the engine fueling. Indirect injection, you don't see that very much, where you have a side chamber that produces the charge of the fuel into the cylinder area. The ratio is the number of times that values have been expressed, specifically in compression ratio, where the cylinder volume at volume dead center versus the cylinder volume at top dead center. Here we have a typical compression ratio of 17:1, so the volume is 17 times compressed. So this volume is 17 times the compressed volume. And diesel engines such as the Detroit diesel 15-liter is 18.4:1. So they're still using 17:18 compression ratio in modern over-the-road tractor engines. The pressure made by the compression stroke as the piston travels up, that is your compression pressure. In a modern diesel engine, it's approximately 600 pounds per square inch. Combustion pressure is the peak pressure developed during combustion. Today's power stroke and today's electronically managed engines is approximately 3,000 psi, and that occurs after top dead center. Our naturally aspirated engines that we see in utility and in the Thermo King used Isuzu and currently Yanmar engines, and Carrier is using Kubota engines that have simple naturally aspirated engines. Manifold boost describes the pressure created by the turbo. Volumetric efficiency is the ability of the engine to breathe effectively. And the fire point or flash point of the fuel vapor is where it has enough for continuous combustion to take place. A cycle is a recurring event. The diesel cycle is typically 4 strokes as the engines turn through 2 revolutions, and that's 720 degrees on the crankshaft. Describing the 4-stroke diesel cycle. On our intake stroke, we have the intake valve is open, and the intake valve is allowing boosted intake air to get into the cylinder, and it travels to bottom dead center at that point. On the compression stroke, the intake valve is closed, the exhaust valve is closed, and the air is compressed to build temperature, and just as it gets to top dead center on the compression stroke, just before top dead center, fuel is injected into the cylinder, and it creates the power stroke. Both valves are closed here, and the power stroke, we have effective pressure of approximately 3,000 pounds per square inch that pushes the piston down and throws the crankshaft. That's also called crankshaft throw at this point. On the exhaust stroke, we have 2 things happen here. The piston is coming up with the exhaust valve open, and the exhaust valve is pushing the light, burnt, dead air out of the cylinder, and that towards the end of the exhaust stroke, the intake valve will open, and the intake valve will introduce fresh, colder, denser air to scavenge out the cylinder as the exhaust valve closes. And that is our 4-stroke diesel cycle. Okay, so we have the intake stroke. Piston's moving down, the intake valve is open, and it's filling the cylinder with air. Compression stroke, the piston is, both valves are closed. The piston's traveling from bottom dead center to top dead center with the intake and exhaust valves closed, compressing the air charge into the cylinder and heating it. The expansion or power stroke, shortly before the completion of the compression stroke, atomized fuels injected into the cylinder, and cylinder and creating the combustion. That pushes the piston down, the power stroke. The exhaust stroke is the piston is coming up with the exhaust valve open, and it's forcing the burnt hot air out of the cylinder. So we have our intake for A, piston's moving down, intake valve is open, fills the cylinder with air, boosted air. Compression, both valves are closed, and as it gets to the top dead center, just before top dead center, the fuel is introduced to create the power. The combustion, the explosion or combustion of 3000 psi pushes the piston down to create the power stroke, and it comes back up with the exhaust valve open, and at the end of that, the intake valve will begin to open, and a valve overlap or scavenging will occur. This is a representation of the compression and power stroke. As the cylinder is traveling in the upward position, moving up, compressing the air, injection occurs approximately 10 degrees before top dead center. We have an initial, in modern electronically managed engines, initial pulse of fuel is introduced into the cylinder to create a flame front before the volume of fuel is added, and that occurs between 10 degrees and by 3 degrees top dead center. A little bit later on, we have ignition, and from 3 degrees to 15 degrees after top dead center, we have peak cylinder pressure of 3,000 pounds per square inch. That throws the crankshaft down. Approximate maximum throw power is attained approximately 90 degrees after top dead center. And down here you see that the exhaust valve starts to open and allows the burnt air to go out into the exhaust manifold. The pressure differential is what allows the exhaust to work, because on the exhaust stroke the pressure is greater than the exhaust manifold, so the exhaust gases are going to travel to the exhaust manifold. Inertial, the piston comes to a standstill at bottom dead center at completion of the power stroke. The displacement, as the piston's forced upward through its stroke, it positively displaces the combustion end gases above it. And scavenging occurs, as we talked about valve overlap. This is when the intake valve will open towards the end of the exhaust stroke, and that allows the exhaust gases to be cleaned out of the cylinder, also known as scavenging. This is what the circular pattern looks like as the scavenging occurs. The exhaust gases, the intake valve will open, and the scavenging occurs, the exhaust valve will close. It's pretty straightforward, but that happens in gasoline and diesel engines on every cycle, every 4 cycles. The 2-stroke engine cycle, you always have a power stroke. Every time the piston comes down, you have a power stroke. The air is drawn in through the crankcase on your 2-stroke engine with exhaust ports, because the piston has holes in the liner has holes in the side, and that allows it to fill. And the compression occurs on the upward stroke, and the fuel is introduced, creating the power stroke, and the exhaust occurs as the piston travels down and then back up into the exhaust stroke. The 2-stroke cycle is 360 degrees. Our 4-stroke cycle is 2 rotations of the crankshaft, which is 720 degrees, but the 2-stroke occurs in 360 degrees, and it's represented in this circular chart here. The concepts and the components are the same in compression ignition, or CI, that's your diesel engine, and the same as the auto spark ignition, or SI cycle engine. We have engine housing components: engine powertrain, engine feedback assembly, engine lubrication circuit, engine cooling circuit, engine breathing system, and engine fuel management system. Here we're going to take a look at a Cummins ISX CM871. We have one in a running stand in the diesel shop. Take a look at this. It's showing the cooling system flow. Here it's going from the water pump. It's traveling through the, here it's showing it's going through the EGR cooler and the turbo and an oil cooler and through a plate behind the ECM. Here it's showing it traveling through the engine block, around the liners and through the, also through the cylinder head. The injector cups have coolant flowing behind them. And they're showing this here with the injectors, and the fuel system is part of the cooling circuit. The airflow system going from intake through the turbo, through the charged air system, through the charged air cooler in the front of the engine. So we're starting at the turbo, take the air in, we're going through the charged air cooler, and we're going into the intake side of the engine. We're showing the oil flow system, the lubrication, starting in the oil pan, picking up oil with the oil pump and putting it through galleries that'll lubricate our crankshaft mains, and then up into the cylinder head to lubricate the overheads. We're also lubricating the turbo in this example, and we have oil flowing through they're showing the overheads here in the cylinder head, where we have oil going through galleries in the rockers, and that can be seen in this diagram here. The exhaust system flow for the EGR has exhaust gas going through it through the EGR cooler. It's going through the controller, and it's going to put a percentage of the EGR into the intake to cool the combustion temperatures. The turbo is showing how the turbo exhaust flows through the turbo from the turbine to the impeller of the turbo that's on the Cummins engine. Here's a simplified look at the exhaust flowing through from the turbo. It's entering the diesel oxidizing catalyst and the diesel particulate filter, and engines from 2010, it travels on to the SCR, selective catalytic reduction chamber, which is next. Exhaust after treatment has what's called the 7th injector in this engine, and it's going to take fuel from the fuel system, which goes behind the cooling plate behind the ECM in that model. It goes through a system where it will inject fuel into the exhaust stream to build sufficient heat for the after treatment system to work correctly. It needs about 500 degrees at the DOC, and that is accomplished by injecting fuel into the exhaust stream. Even though this information is theoretical in its nature, it's important for technicians to understand what's going on and what this terminology is and why it's important. Thermal efficiency, how the engine manages heat. We have to get the heat has to be removed from the engine, and the heat has to have heat transfer in a combination of exhaust gas and the water jackets and the radiant heat from the engine itself. So we have oil jets that allow us to cool the engine from the bottom. We'll get into that later on in this course. We're going to see how the cooling system is critical in maintaining the operation of the engine. We have ability for engines to create power and torque, and the tendency is to rate gasoline fuel auto engines by their total displacement, but diesel engines having higher compression ratios tend to be under square. That means that the stroke is greater than the bore. Almost every medium and large highway tractor engine is turbocharged and has manifold boost. Every engine since 1991 is a 4-stroke engine. 2 strokes were made illegal. The 71 series Detroits were in tractors up until 1991. They're no longer compliant. That the engine cycle, the 4 strokes, occurs over 2 rotations of the crankshaft. That's 720 degrees. That the 2-stroke engines enable a power stroke every time the piston goes down. In theory, they have a potential to produce more power, but in practice, it's not obtainable, and they're no longer certified for highway use. Mean effective pressure is the pressure acting on the piston through the 4 strokes of the cycle. It's essentially the pressure created inside the cylinder during combustion, subtracting the other pressures required to make the rest of the 720-degree rotations. Okay, fueling is managed to produce peak cylinder pressure somewhere between 10 and 20 degrees after top dead center. The cylinder pressure drops throughout the power stroke, but the throw mechanical advantage, the rod throw angle, is at 90 degrees, providing unloading of the force to the crankshaft and ultimately to the flywheel. The engine attempts to convert potential heat energy into useful mechanical energy. This is known as thermal efficiency, and the heat energy of a fuel is not converted into kinetic energy is rejected heat. That's approximately 60% of the fuel's nature. Rejected heat must be dissipated by methods of cooling and exhaust.